All right, so now in this section, we're finally ready to start talking about the stationary states of the hydrogen atom, or the solutions to the time-independent Schrödinger equation. In the last section, or in the last video, we talked about the energies, which are indexed by this principal quantum number n, and they go like this if you write it in terms of the Bohr radius, or if you write them in terms of the Hartree, it's minus e Hartree divided by 2n squared, or it's in terms of the Bohr radius, minus h bar squared over 2me times a naught squared times n squared. And the allowed values for this n go from 1 to infinity, so 1, 2, 3, and so on. And the stationary states are indexed by 3 quantum numbers now. So there's the principal quantum number n, the angular quantum number L, and the magnetic quantum number m sub L. And all of these go into defining the actual eigenstates, because now you have the radial part. So the radial part carries 2 different quantum numbers, that is the principal and the angular. And then you have the spherical harmonics at the back, which carry L and m sub L. So each of these carry 2 quantum numbers, and you have the L in common for these 2. Okay, and now based on the way that you end up solving the radial equation, you find that the allowed values for L lie between 0 and n minus 1. And we know from the spherical harmonics that the allowed values of m sub L are for the magnitude, or the absolute value of m sub L to be less than or equal to L. Or in other words, m sub L can go from minus L up to plus L, which gives you 2L plus 1 different values. Let's start by talking about what the solutions to the radial equation look like. Okay, so now let's go through this piece by piece. So the first piece we have on the left, highlighting in green. Now you notice that this part does not depend on r explicitly, and so this should tell you that this is just a normalization constant. So this is here to make sure that the norm of r is 1. Now the next term that you see is this r to the L times e to the minus r divided by n a naught. So a couple things. So first you notice that this a naught is popping up again in the solutions. We previously motivated a naught by saying that it's sort of a natural length scale for the hydrogen atom. And here you're seeing some evidence of that because the exponential has an explicit a naught in this. But what this term does together, so this is r to the L and e to the minus r. So this here takes care of the asymptotic behavior. So this tells you what will happen as r approaches 0, and also what happens as r approaches infinity. And so the overall gross behavior of the whole term is determined here, but the detailed behavior will be determined by the next term. Now the last term is this big L of 2n plus 1 and n plus L. Okay, so these are what's known as the associated Laguerre polynomials. At this point, these special polynomials that keep popping up should start to sound a little bit like a broken record, right? So the associated Laguerre polynomials are a special set of polynomials that have their own orthogonality properties and that just naturally pop up in the solution of this and some other differential equations. And just like all of the other special polynomials that have come up previously in the class, we are not going to do any detailed derivation of these polynomials, but a lot of the same things, a lot of the same properties that the other ones have, the Laguerre polynomials will also have. So they also have some closed form recurrence relations. So if you know a couple terms, then you can figure out the higher order terms. They also truncate. The Laguerre polynomials have a maximum order, which ends up being
n minus L minus 1.
which we'll see some examples of in a second. And again, we see that just naturally out of this, we see that the natural distance for a natural distance for the hydrogen atom is related to the Bohr radius, right? So here you have this r over a naught popping up again. So now let's go through and write out some of the first few solutions to the radial equation. So r and l for low values of n and l. So the first one, and there's just one of them, is you have r of 1, 0, which means n is equal to 1 and l is equal to 0. This is a function of r. And this is the simplest one. So this is 2 times 1 over a naught to the 3 halves times e to the minus r over a naught. If we're to the n equals 2 values, you have 2 of them now. Now for the n equals 3 solutions, you have 3 possible values, right? So you have n equals 3 allows for l equals 0, 1, or 2. Now let's notice a few things. So as we said before, as n gets larger, you get a 1 over n factor in the exponential part of the solution, which means that as n gets larger, the long tail of these will start to decrease a little bit slower, right? So this factor here will get a little bit smaller, so it's e to the minus smaller magnitude number, which means that it will extend further and further out at large R. The other thing to notice is that for each of these, you always have a polynomial times an exponential, but some of this polynomial comes from this r to the l out front, and some of it comes explicitly from the Laguerre polynomial. And for a given n value, for n equals 1 and for n equals 2 and 3, for example, the maximum total value of r on this polynomial is always fixed, and it's always equal to n minus 1. For n equals 2, l equals 1, there is a maximum order of r to the 1, and the same for n equals 2, l equals 1. But the difference is how much of that is coming out front and how much this is coming from the associated Laguerre. And you see the same thing for n equals 3. Each of these terms stops at the r squared at most, right? So you have r times 1 minus r over here, and then you have an r squared explicitly here and here. And then finally, let's look at the order of the Laguerre polynomial. So the Laguerre polynomial for the n equals 1 solution is basically trivial. It's just 1, so it has really nothing going on. For n equals 2 and l equals 0, it has order 1, goes up to a power of 1. For n equals 2 and l equals 1, again, it's kind of trivial. So this r comes from the asymptotic part, and then you just have the 1 again. And then if we see the same trend going up here, so 3, 2, so n equals 3, l equals 2, there is basically just a trivial Laguerre polynomial. You decrease l by 1, and you get now up to power of 1 in the polynomial, and you decrease l again, then you get up to power 2. And so this is telling you that these Laguerre polynomials have values of r up to n minus l minus 1, right? So when you have n minus l is equal to 2 here, and you have a first degree polynomial, n minus l is 1 here, and you have a 0th degree polynomial, n minus l is 2 here, and you have a first degree polynomial, n minus l is 3 here, and you have a second degree polynomial. And then these will also come into play because these end up defining radial nodes. So if you have a nth degree polynomial, you can possibly have n nodes. Okay, now the final thing to note, although it requires some explicit calculation to see, is that all of these polynomials, each of these ones that I've written, are orthogonal with respect to each other. So what this means is that if you look at the inner product and you define it like this, okay, so this is the inner product between two different radial functions with possibly different n, so n and n prime, or L values, L and L prime. And now they have to be multiplied by this weighting factor, and this weighting factor comes again from the volume element in spherical coordinates. So if you look at this inner product where you multiply the two functions and then multiply the weighting factor, then the result that you get from this is that you get delta n n prime times delta l l prime. And so this is telling you that unless you have exactly the same values for n and n prime, then you will get 0. And if you do have exactly the same values for n and n prime, and also for l and l prime, then you just get 1. We'll leave that as that for now. And then in the next section, we'll pull together the radial solutions with all of the angular solutions and start talking about the complete eigenfunctions of the hydrogen atom.